Okay, this chapter is about how to design the input signals for system identification experiment. This video clip is recorded on Wednesday, August 18, okay, by Jitkomut. We're gonna discuss about common input signals in system identification. These are functions that commonly used in engineering applications as well. Step function, sum of sinusoid with different frequencies, sequences generated from AMA process. And the last one, this is pseudo random binary sequence or PRBS. Okay. Uh, when we talk about this, when we will examine correlation function properties and its spectral density property. Okay, and the most important concept of this chapter is the property of input signal that is called persistent excitation. Okay, is a degree to which to explain if our input signal is sufficiently informative for the experiment, or basically how can you choose a good input for system ident. Okay. If we look at the overview of the experiment, when you have a system, you have a physical system. Then of course you don't know its model. You don't currently you don't know mathematical description. Okay, but the thing is, what you can do is you can access to this system in a sense that you can feed some input and then you can measure the output. Okay, so by doing that, let me represent it by having this frequency response as a relationship between u and y, represented in frequency domain. Okay. Of course, you can obtain this graph from the experiment. Okay, when you can apply u as a sinusoidal system at a certain frequencies, and then you measure y. You get 1 point on the Bode plot. Okay, and you vary the omega for for a number of frequencies, and then you get the whole thing. Okay. Then if we look at, in this example, if we look at the Bode response, I mark the bandwidth of the system. Okay, I mark the bandwidth is around here. For generating this graph, I actually put the transfer function g with some expression, and I use the Bode command, right? This is simulation, but of course, as I said, in real application, this information can be obtained from the experiment. And the bandwidth is around 144, okay, radian per second. So what does it mean? It means you see that the gain, the Bode plot, the top part explain the gain of your transfer function as a function of omega. The bottom one explain the phase, right? And as you see, the gain of G drops when omega is large, and obviously when omega is higher than the bandwidth, the gain is very low. Here is in dB. Okay, so what can you expect from this from this given information? Of course, in this slide, I give some examples of how you would see at the response y as I apply input from various type. The first one, when we learn about linear system class, of course, we commonly talk about step response. Okay. Step response is what? We apply a constant input. Here's in the thin blue line, and the green line is the output. Okay, this is how it looks like at the output. The system rises, okay, and then decays and converts to a constant. How about square wave? Square wave is a common type of input as well. There's a, of course, when we do the lab, we have signal generator, and this is one input type that we can generate from those equipments. The green, the orange one is the response of Y. Okay. The third one is the mix of sinusoidal. Is a mix of psi with different frequency. You see that it's like there's a multiple envelope. Okay, and see that. So this is the sinusoidal with higher frequency, and the blue one is a sinusoidal with lower frequencies. Again, the orange one is a response. The last one is the response to the white noise. Okay, white noise. If you haven't familiar with this term, again, review the stochastic process video. And white noise is a random signal that has no correlations with the correlation between UT and US is 0. Okay, so what happened now has nothing to do with what's gonna happen next. So it is the most unpredictable signal, white noise. So you see that it's all very highly fluctuated, and your result, it seems like your result, your response Y is smoother, kind of smoothened a little bit, but still contains some fluctuation. Okay, so this is what you see in time domain. How about in frequency domain? What I plot here, it is the power spectrum. The power spectrum is is a function that you examine in the frequency domain. Okay. It is the power because you can look at the signal when you take the Fourier transform, and then you take the magnitude, right, square. So it represents the power, and of course, in signal processing, the power of a signal in time domain and in the frequency domain are preserved; they are equal. Now let's take a look at the results here. When you consider the step response, what you see in the frequency domain, the step input is a constant, so it has only the component in DC mode at zero frequency, as well as the output. Okay, for square wave, what do you know about the square wave? Napat, can you answer that?
อะไรนะครับอาจารย์
That's the question. When you have a square wave, for example, this is a square wave at, a square wave has a period, right? So
yes,
okay, and a period corresponds to a frequency. But the thing is, as you have learned before, okay, what are the frequency components of a square wave? If this period t correspond to some f naught. But if you take the Fourier series of the square wave, what do you get?
get a sinc function.
Okay. How about someone else? Can someone else have more to discuss? City Park?
Is a sinusoidal with different amplitude.
But is it a single sinusoidal?
Many sinusoidal with many frequencies.
Yes, and what are those many frequencies? What do we call it?
Mixed. They are mixed.
yes, they are mixed. You remember the concept of harmonic frequencies? It's not that, okay, for the square wave, if you look into the frequency domain, it doesn't contain only the frequency F naught, that represents the period of the square wave, but it contains so many others. That is called harmonic frequencies. And yes, and that's what we see here, the blue one, you see, square wave, and there's a mixed frequency, and you can also see it from what? From the output. Okay, but it seems that the power of the output seems to be decreasing for higher frequencies. Okay. For mixed side, okay, I don't have the information in the slide that, I mean, what are those exact frequencies of the mixed side? But if you look at this plot, okay, it seems that I generate the signal of sinusoidal at these frequencies. Okay, at 100 hertz and somewhere around here, less than maybe 10 or 20 hertz. So again, in this plot, it for the mixed side, it explained that if you put a sinusoidal input at WK, at omega K frequencies, then you're gonna obtain the output, right, at the exactly omega K frequencies. There can be no other frequency modes. There can't be. Okay. Is this okay? Is this understandable? Is this a fact, right? Remember that we reviewed it last time. If you put psi at at the frequency 10, right? You will get something that, of course, contains sine of 10, and of course, maybe another term with the cosine. But there must be at the frequency 10. There cannot be sinusoidal at other frequencies. Okay, and the gain represents, of course, how your system attenuate you at that frequency. Okay. Now, if we look at the last case, is the white noise. This is the white noise property. If you look at the power spectrum, the spectrum, which is the blue line, is flat, which means the power spectrum seems to be constant over all frequencies. I mean, theoretically, it's a constant, but of course, this is the simulation. Okay, and the orange one is the power spectrum when you apply white noise as the input. So there's a kind of the decreasing trend here at the higher frequencies. So so if we look at the frequency response of the output after you vary various types of inputs, what does it suggest you? Remember that the goal of system identification is to estimate the model G. We would like to extract all the information in G. Okay. If G is complex, G has many modes, many dynamical modes. For example, if G is order 100, right? There will be of course 100 poles. Those poles characterize the response. Some poles may be fast, some poles may be slow, right? Some poles may be complex conjugate pair that represent oscillation behavior. Okay, and those poles correspond to what? And that's what we call the frequency mode of the system. Okay. If we look at here, for example, if we look at the step response, ping, what do you see? The if you apply the step input, you only get, if you look at the frequency response result, you only get the response at 0 frequencies.
Yeah.
So is it informative for you to say something more about the system G?
The system G is maybe it is working in the, if the input in the frequency like that and output it's just a constant something again.
Okay, Ping, what if we look at the spectrum here, you will see the gain. I mean, sorry, the power of output at 0 frequencies, right? And you see the power of the input. Sorry, you see the power of input and the output at 0 frequencies. So somehow you can approximate the gain of G at 0 frequencies, right?
Yeah, it should be again.
But then what about other frequencies? Right? This is only thing that you can conclude from the first case, from the step response case, right? Or maybe move to Kanatat. Okay. Look at the response of using sinusoidal.
Yes.
Kanatat. Okay, if of course, you only get the response of Y at what frequencies? At omega k, where the omega k is the frequency of your input U, right? But what if, I wanna, because the whole point is I wanna know the characteristic of my system G. If I wanna know the gain of G at, let's say here, at 70 hertz, can I get that information from this graph? Kanatat.
I think yes, you can.
I can. Okay. How? Oh, I'm asking how. How can you get the gain of the input at 70 hertz?
Maybe you have to use from another hertz and maybe just predict over combine something.
Okay. No. The setting here is that if you apply UT as a sinusoidal that has the mixed frequencies, but the frequency lists are given, and just like in this particular example, the frequencies of the sinusoidal is here, and here at 100 hertz. That is a given situation, okay? But then, of course, because the response will be, the response of Y will contain only the frequencies that are that correspond to the ones from the input. So it means that if you can't say anything about the gain of the input or the phase of the input. The gain of the system or the phase of the system at in this example at 70 hertz, because you don't have that information. Okay.
Okay.
So, and of course, when you do the system identification, you don't remember that you don't know. Probably if you don't plot this Bode diagram first from the experiment, you kind of, I don't know the bandwidth of the system, right? When you estimate the model, when you estimate the system, you don't know its frequency components beforehand. Okay, so it means that, oh, if you use a mixed sign, you need to make sure that, oh, the list of omega k must correspond to frequency within the bandwidth of the system. Okay. How about the white noise? For white noise, because white noise has a flat spectrum. So the flat spectrum means that it contains a constant power across frequencies. So it can stimulate the system at all frequencies. So that's why you can get the response of output, you know, at all frequencies. And then now, if I look at this graph, I can say, oh, the gain of my G at 70 hertz. Okay. So I'm gonna measure the output gain at 70 hertz, right? And divided by the input gain at 70 hertz. Okay. So the whole point is that when you choose the input, okay, you should make sure that the input should be informative enough and it should stimulate all the frequency modes of the system, all the significant frequency modes of the system. Okay, and that's the whole point of this lecture. So you see that for step response that is commonly used, this is not an appropriate signal for any type of model, especially for complex system. Okay, so now I'm gonna go over each input signal one by one and explain its characterization, explain its spectral property, and correlation function property. Okay. The first one is very simple. Step function. Step function is a constant for a positive t. Okay. Of course, when you learn about a linear system, we often start with a second order system, right? Because it's simple. Its time domain response can be derived in closed form, so you can associate the rise time, the overshoot, the static gain with the system pole, with the coefficient of transfer function, and you can examine these time domain specification from a step response, if you can recall, right? When you learn in linear control system theory, right? Like, oh, this is my step response, this is my overshoot, right? This is my settling time, my rise time, all those things. Okay. It's often useful for a system with a large signal to noise ratio, because everyone is familiar with this term, SNR, signal to noise ratio. Can someone give me some short description? Maybe Totok? Totok?
I'm sorry, Ajahn, I don't familiar with this term.
Signal. Okay. How about I don't know. Kanatat? Signal to noise ratio.
Yes, it's like a efficiency of the signal that have how many noise when you compare to the whole signal.
Okay. Like you have the intrinsic signal, right? The real one. Okay. But then you want to transmit this signal, but then there's a noise corrupted, right? And so what you observe is actually the corrupted one. So signal to noise ratio is a common term in signal processing. That is a ratio between the power of the intrinsic signal divided by the power of noise. Okay, so in engineering application, do you want a signal with a higher SNR or a lower SNR? Kanatat.
Lower.
Huh?
No. High.
High, right? we want to have the smallest amount of corrupted noise as possible. Okay. It's okay. I just would like to recall to that definition so that come back here. Of course, if when you measure the step response from a sensor from the physical system, it doesn't look as smooth as in this graph because this one is theoretical, right? What you're gonna see is actually this when it's corrupted by noise. Of course, in real life, then it's gonna be like when you read the graph. So of course, the quantities like rise time, overshoot, and settling time will be kind of, it has to be assessed by the user. And then when the noise comes in, it's just hard for you to get the appropriate values of those specifications. And the step response rise a lot when you would like to characterize the system property, where that system can be represented by the first order plus time delay. Okay, this is first order system. This is the time delay, e to the minus ls. The value L is the time delay. The DC gain, okay, is first order because it has one pole here at minus 1 over tau. Okay, a lot of chemical processes can be represented in this way. Okay, and also some higher order complex process can also be approximated in this way. So what they actually do, what they commonly do is to get this is step response, and we call this one reaction curve. Okay, so you apply delta U as the input, and this is what you observe at the output. Okay, so there's a method that is a graphical method that help you determine the time delay. Okay, because you apply the input at time 0, but your system, your output start to rise around here. So there's a delay. And then, to obtain this parameter, you're gonna see what is the inflection point. Okay. So the point where the slope of this line is highest, and you draw this tangent line. And when it intercepts the time axis, okay, that's how you get the delay. Okay, and then this slope, this straight line, when it intercepts with the steady state value of your output, which is the value of k delta u, this is something you can read from the graph, then you can obtain the parameter k. Okay, so when these tangent line intercept the horizontal line here, you draw it here, so then that you get the time constant tau. Okay, so this is called a graphical method. So you can look at further reading in any linear control system book. Okay, but I just would like to mention that, okay, when you apply the step response, you can read off the system parameter that associated with simple description, like the first order model. Okay. Next, the sum of sinusoids. Okay. The sum of sinusoids has this form. It's a mix of sinusoidal with different frequencies. Omega k, phi k is the phase shift, ak is a magnitude. We're going to choose the frequencies so that, of course, all of them are distinct. They are not the same values, and you choose it from the interval 0 to pi. Okay. Okay, that's a description. And then, okay, what we're gonna do next is, okay, if you have the sum of sinusoids, let's take a look at the autocorrelation function and the spectrum. You can expect that, okay, if I have the sinusoid at omega k frequencies, right? I mean, intuitively, you would expect that at the frequency, at the frequency domain, you would see something related at omega k, and that's gonna, of course, that's gonna show up in the analysis. Let me recall that when we talk about linear stochastic system, random process. All right. Please refer to that video. We talk about autocorrelation function, and we talk about spectral density matrix or spectral density, which is the Fourier transform of autocorrelation function, right? And it seems that, oh, this concept applies to a random process. But when we look at this situation, all you have seen is that, oh, the step function, this function is not random at all, right? The sum of sinusoid, this is not random. That's why actually it is developed in the framework that, okay, there's a term quasi-stationary process. Okay, it's actually a signal that is deterministic, but there's a definition that analogous to stationary signal. So please refer to the book by Lung. This is the main textbook of our course. And if you have my Thai book, it's in the appendix, all right? Okay. So when we characterize the quasi-stationary signal, we're gonna use the tools that can be implemented with deterministic signal and also in practice. For example, we know that theoretically autocorrelation function is yt plus tau times yt, right? Expectation. And that expectation should be done corresponding to the PDF of yt. Okay. But then for deterministic signal like this, and with the definition of quasi-stationary, we're gonna use the operation summation instead of expectation, and that's going to be the time domain sum. Mm-hmm. So, and that's what we're doing here. Okay, for example, you have the sum of sinusoids. All right. First, I would like to examine the mean of sinusoidal function. This is not the ensemble mean, as I said, because your UT is not random. So we take the time average instead. Okay, so this is the average of sinusoidal over n data points, and then we're gonna allow n to be large enough. Okay, with some details of how you characterize this limit. All right, please refer to the reading. A lot of mathematical details in this chapter will be omitted for reading in Soldier Storm book and also in my my book at the appendix. Okay, if you take the limit of the average it seems that it turns out that the mean is a sine phi, okay, the magnitude and the phase, okay, when omega is a multiple of 2 pi, but it becomes 0 otherwise. Okay, so what does it mean? It means that, okay, with this given information, if you have a sum of sinusoidal inputs, you can just make it 0 mean, right? Because having zero mean signal is simple. You don't have to worry about, I mean, so you can use the second moment and the like the covariance function and the autocorrelation will be the same if the signal has 0 mean, so that you don't need to worry about subtracting mean before the analysis. Okay. So you can just pick the first frequency. Remember that your sum of sinusoid, you have a choice of choosing these frequencies. You just choose the first one that is different from 0. Okay, and then you apply this result that, so the mean will be 0 automatically. Okay, so from now on, we're gonna assume that your UT as a sum of sinusoid has 0 mean. Okay. Okay, so next we look at this spectrum. Again, just like you see, okay, instead of characterizing autocorrelation using the expectation, we use the time domain sum here. So it's an autocorrelation at time gap tau. All right. So this is kind of the convolute term. So you shift u to at time t to t plus tau and multiply with ut, make all the average over n time points, and you allow n to be very large enough. Okay. Again, there's a detail, a lot of detail here, but I just state the final result that your autocorrelation function turns out to be the sum of cosine at omega k frequencies, where the coefficient ck is simply the magnitude of the sinusoidal input square and then half. Okay. Recall again, what's the m again? M is the number of frequencies component in the sinusoidal input. If omega m equals pi, from the analysis, we need to modify cm a little bit, and it turns to be am square, psi square phi m. And from this result, it's very automatic. If you have a sum of cosine, right, at a certain frequency, the spectrum, which is the Fourier transform of autocorrelation. If you are not familiar with this, again, watch the video or just read the book, Wiener-Khinchin theorem. Okay, spectrum is the Fourier transform of autocorrelation function. These two guys form a Fourier pair. And of course, you would see this is a known result from Fourier, right? You have cosine, and you get the delta function in the Fourier transform at two frequencies. Hold on. Okay. The call from the department. I need to pick it up. Okay. So with this result, you have a mix of sinusoidal inputs at frequencies of 0.4, 0.8. Sorry, this is a typo. This is supposed to be plus. Okay. How many frequencies component we see? 3, all right, 0.4, 0.8, and 2. Okay. And this is what you see at the time domain. And this is autocorrelation function. These might not look uh, uh, close to the mathematical representation we see here, because it's supposed to be the cosine, the sum of cosine. I'm not sure if you see here, but if you just connect the dot, you will see that you will see many envelopes in the sequence. All right, so like it contains like 3 frequencies. And of course, it's much clearer if you just take a look at the spectrum exactly at 3 frequency, at 0.4, 0.8, and 2 radian per second. It's a good exercise if you can reproduce a plot like this, because it requires some concept of signal processing. Like if I give you a time domain signal, can you compute autocorrelation, like from like using computer codes? Okay, like the theoretical value, just verify it using the software like MATLAB, like Python, and see if it's agree with your theoretical expression. For spectrum, there's you can either take the Fourier transform and then take the modulus square, or you can just compute the spectrum directly from existing built-in commands. Okay. All right. So I would like to break the video first before we keep discussing more about other input signals.